Estimations unit. And this is lesson 3. We're talking about parent functions, the parent functions that you have to be able to recognize. The first part of this lesson really doesn't have notes for you to take. You need to watch and learn. And then we're going to go over and fill in some charts for you to learn which graph is which. This is really more memorization than anything else. So let's get started. First, before we can look at transforming graphs of quadratic, absolute value, cubic, and square root and cube root functions, we must first know what each parent function looks like, the original function. So x squared, f of x equals x squared, or y equals x squared. If x is -3, y is 9. If x is -2, y is 4, and so on. I simply plug the x value in here and square it to get the y value. Now, I've graphed it over here in blue. Notice that you start at the vertex, the center. You go right 1, up 1. You go right 2, up 4, and right 3, up 9. This is called the parent pattern, starting at the vertex, wherever the vertex is. Now, because it's symmetrical about the y-axis, whatever you do on the right, you do on the left. So as soon as you have the right half graphed, you can reflect it over the axis of symmetry, the vertical line that cuts through the vertex, and graph the left side. Quadratic function. An absolute value function is denoted by the 2 vertical lines on either side of the x. Here, the absolute value of any number is the positive version of the number. So the absolute value of -3 is 3, of -2 is 2, of -1 is 1, and so on. Again, notice you have a vertex or a turning point. The pattern here, right 1, up 1. Go back to the vertex, right 2, up 2. Back to the vertex, right 3, up 3. Symmetrical about the y-axis, so what you do on the right, you do on the left. Here is our parent pattern. Square root function. The square root function doesn't have a vertex. It has kind of a starting point. I put vertex in quotes because it's not really a vertex starting point. It's still 0, 0. Notice vertex and starting point is still 0, 0. Now this one, the square root of 1 is 1. 2, not a pretty number. 3, not a pretty number. The square root of 4 is 2. The square root of 9 is 3. So I'm going to use nice numbers to make my pattern. My pattern is the starting point, our quote-unquote vertex, right 1, up 1, right 4, up 2. Notice all of these are right 1, up 1. Okay? All of these are right 1, up 1. So that's how you're going to figure out stretches and compresses. So square root function, it looks a little bit different. It's not symmetrical like absolute value and the squared or quadratic function. Here we have a cubic. Don't know why I made that so teeny tiny there. Make it a little bigger for you. Right, for this one, we have a turning point is again 0, 0. That's our quote-unquote vertex. Really not a vertex, but a turning point. The pattern, 1 cubed is 1, 2 cubed is 8. So 1, 1, 2, 8. The right 1, up 1, right 2, up 8. Remember, you're always going back to the vertex before you move right. Now, the difference here is what you do on the right, you do the opposite on the left. So if you went up 1, you go down 1. Okay, so it's not quite, it's got point symmetry, not line symmetry. The cube root function. Again, notice, very similar to the cubic, but it does have a little bit of a difference here. Instead, we still go right 1, up 1, but now we go right 8, up 2. And then to the left, instead of going up, we go down. Again, point symmetry. We still have the right 1, up 1. The nice thing is all these parent functions, the first step from that starting point is always 1, 1. Now, before we can look at transforming them, you've got to know the parent functions and the parent patterns for these 5. There will be more added on as we go through this year. Right now, we're going to focus just on the quadratic, the absolute value, the cubic, and then the square root and the cube root. Okay? So you've got to have these down pat. Now we're going to go and we're going to fill some information in from a handout. That handout should look like this. The parent function is linear, f of x. Linear is kind of weird, okay? It's also known as our identity function. And there's the graph, right one, up one, right two, up two. What you do on the right, you do on the left. You do the opposite on the left. The domain is all real numbers. The range is all real numbers. When you're looking at the domain and range and you're saying all real numbers, if it's written in interval notation, that would be negative infinity to positive infinity. Okay? Now here the x-intercept and the y-intercept are both 0, 0 for the parent function. There's only one root. The end behaviors. As x goes towards positive infinity, y goes towards positive infinity. As you go negative on x, you go negative on y. So that's the end behaviors. It is continuous. There's no break. Absolute value function. That's our V shape. Again, the domain is all real numbers. Y, however, goes from 0 to positive infinity. The x-intercept, 0, 0, y-intercept, 0, 0. It has a maximum number of roots, could be 2, because notice if you pull this V down, I cross the x-axis in 2 places. I could also push it up and not cross it at all. But you have to recognize that you could have 2. End behavior, as x goes to positive infinity, y goes to positive infinity. As x goes to negative infinity, y is going to positive infinity again. This graph is continuous. Continuous means I can draw it with one stroke of my pen or pencil. I don't have to pick it up. Next up, quadratic and cubic. Blah. So did I give a pattern back here? Yeah, the pattern, I wrote the pattern off to the left, just so that you would have it. You might want to make note of it on your paper. Here, the quadratic and the cubic. And you're going to graph these in, and then you're going to note the quadratic domain is all real numbers. The range is from 0 to positive infinity. End behavior. This part tells you where x is going. This tells you where y is going. I'll put a little y here in case, okay? That's what you think of when you see f of x is the same thing as y. Alrighty? So now it's continuous. I can draw it with one pen movement. Parent pattern right here. Parent pattern right here. You have to have 5 points when I ask you to graph, unless it's been stretched or compressed so much that you can't get the 4th and 5th points on. The square root function is a little bit different. You have to have like 3 points. Okay. Next up, square root, cube root. Similar kind of guys to the square and the cube, or the quadratic and the cubic. Again, continuous, continuous. Here's all the information that you can fill in. Okay. Now, the one thing I did want to show you back here with the cubic, I could have as many as 3 roots. A cubic can, it can do this kind of thing. So I could have 1, 2, 3 different roots. We will look at cubics a little bit more later when we do more in polynomials, but it can have 3. So you do want to note that down. Continuing on, our square root and our cube root. Leave these here so you can pause the video and graph them, make all the notations that you need to. One of the things about this, again, it's memorization, and it's graphing the parent function several times over again until you have it down. What does it look like? What is its pattern? How to do it. So we're going to be doing several of these to get you used to it. Now when we get past the cube root, we have a reciprocal function, an exponential function, and a logarithmic function. We will address these in future units. I don't want you to get confused with these. We're not going to get into how the patterns or anything of these right now. These will come in future units. The thing about these, we will have down pat transformations. So graphing these will move very quickly in future units. All right, I believe in addition to the quick one-pager, you also have a comic book of parent functions to fill out and color in, and again, more practice getting to know these parent functions. Good luck.